Monica.
Hello, good morning, everybody. So we're happy to welcome you to the new course by Eric Perlmutter from IPhT on the space of holographic CFT. So before letting him speak, I just wanted to make a few quick announcements. So first of all, video recordings of the live stream will be immediately available on the IPhT YouTube channel. There will be lecture notes for the course maybe in a week or so. So check the course website. Questions are welcome. So from the in-person audience, of course, that's trivial. From the online audience, please unmute your microphone, and we can also see you if you want to put your picture. So please do that. Then important for students who need a final certificate of presence. So the in-person students have to sign this form every time for every course that they attend. The online students, when you log in into the video conference, you have to put your last name as part of the nickname. And just to make it very clear, telling us that you're going to watch the YouTube video later does not count for course credit. So I hope that that will save us a number of emails. At some moment, there's going to be a 10-minute break. So since we have the online audience, please be back on time. And after the course, there's the possibility of having lunch with the speaker. So we will be offering lunch to whoever doesn't have an IPhT card, and please come to us to collect one of these yellow cards for lunch, and then follow us to the car. Okay, so that being said, we're very happy to have Eric Perlmutter. So Eric did his PhD at UCLA in 2012 with Per Kraus, and then he did postdocs in Cambridge, Princeton, and Caltech. And then he joined the IPhT in 2020, and he's going to tell us about things connected to his work on CFT bootstrap and
Thanks, Monica. Yeah, I appreciate the introduction and indeed the recruitment to be here in the first place, which Monica was an important part of. So I'm super happy to be here at IPhT in general. I'm lecturing this course, which is a fun aspect of life here. So I hope to put on a course that is useful and fun and might motivate you to even work on these topics. So let me say, so there are 5 lectures. This one will be something like an overview, in a way, of the whole picture that I'm trying to paint. The next few will flesh out some of the details. And the last one will be a bit self-contained. I'll say a bit more about this in 10 or 15 minutes. And so also, looking around the audience, it's clear that the familiarity with this subject varies widely among the people who are here. And so I'm aiming this less at specialists, let's say, because I think that's not the mandate of the course. And for that reason, there will, of course, be some computations and some technical details, but I will try not to make that at the forefront of what I'll be talking about so that everybody can get the conceptual picture, which I think is the most important in the long run. So as Monica said, please definitely ask questions. I'm happy to sidebars on whatever people want to talk about. We have 10 plus hours total. I mean, time flies when you talk about holographic CFT, but still, I think we have time to get into some of the thornier aspects of this if there are things we want to ask about. So this is a bit of a broad subject, and it's really at the intersection, let's say, of 2 very big fields, one of which is CFT, in particular the kind of classification approach to holographic theories and the relationship between strongly coupled CFTs and gravity. That's one. That's already a huge topic. And on the other, the conformal bootstrap approach to CFTs, which, again, another huge topic, but which has, I think, informed a lot of the work that's been done to understand the picture of theories of quantum gravity from a more rigorous point of view, at least when these theories are in anti-de Sitter space. So the picture that brings these two things together is facilitated by ADS CFT. It's something like this. So we imagine some sort of space of CFTs. Think of these as parameters that specify theories on these islands of B. In an abstract way, the place where CFTs actually live. Okay, so there's some CFTs specified by some theta, and this is the space of theories in this very artistic sense. Okay, so some of the theories have a finite number of degrees of freedom. Some of them have many degrees of freedom. So let's call that large N. I mean, systems with many degrees of freedom. In a way, we'll specify more today. And within the space of large N theories, there are theories that have certain other nice properties. So there's some overlap between theories that have lots of degrees of freedom and theories where the spectrum, say, of local operators is especially nice. We might call this sparse. That's a little small. The writing will be bigger later. Sorry. But among large N theories, some of them have a spectrum which looks especially nice. It's not gapped in the usual sense, but there are gaps between operator dimensions which are maybe unusually large. And among those, there are theories that have some coupling constant which can be tuned. There are theories which don't. So there's a lot of variety on this side. Now, if you think about the space of possible theories of quantum gravity, for example, as the swamp land program is trying to constrain, then you might draw some similarly vague picture of the space of consistent theories of quantum gravity, consistent with whatever principles theory of quantum gravity must obey. And so now, if this theory of quantum gravity is in ADS, then there is, by way of the ADS CFT correspondence, some kind of map between these two pictures with the basic level you can think of as being equivalent. If ADS CFT says that there is an ADS quantum gravity theory corresponding to each and every CFT, which is a bit of a caricature of the statement, but something like that is true, then these two spaces should map to each other somehow. Yes. First question.
Ricardo expressed many answers, but do you want to be drawing blobs or other points?
Yeah, both. Yeah, both. Thanks. Maybe, yeah, indeed, the blobs are a little misleading, and I would say generically, the theory is a point.
Unless it's supersymmetric.
Sure. Yes. Yes. Thanks. It just comes across.
Yeah, sorry.
Yeah. Yes, please.
What would unitarity of the CFT correspond to on the ADS side?
Yeah, good. So that would correspond to the absence of, tachyonic particles whose mass is too negative. They themselves would lead to instabilities or have negative norms with respect to some gravitational interproduct. And indeed, when you talk about this equivalence, you want to start saying what it means to be a consistent theory of ADS quantum gravity, what it means to be a consistent conformal field theory, and depending on the context or just personal taste, one may or may not want to impose things like unitarity. I think we're safest when we do, but indeed, there's sort of a map between these kinds of choices. So here, there are theories in the space of theories of quantum gravity that look especially nice. So what are the theories of gravity that we can actually write down and play with? Well, of course, general relativity is the example there. And so there are classical theories, there are quantum theories. We can treat general relativity classically, semi-classically. And within that, right, there are choices, and there are theories in which general relativity embeds. So one of those theories is string theory. So some of these theories are string theories, which may contain a GR subsector. They may not contain a GR subsector, so these two blobs don't have to be right on top of each other. They're regime which don't look like GR plus some stuff. Okay, but understanding this map more precisely is one of the missions of the course, and by now we know a fair amount about this. So one thing that will be clear that sort of goes back to the early days of the correspondence. This picture for a second is that a classical theory of gravity corresponds to a large N CFT, but they don't all need to look like GR. Okay, so some of them may be relativistic, some of them may not be. There may be some more complicated thing where corrections to GR are order 1 in the appropriate units. And so we'll understand that in more detail in the coming days, hopefully by the end of today. All right, so now one way to tell this story is that ADS-CFT has been around for 25 years, and let's say for the first 10 years, the arrow went this way. Okay, so we were doing simple computations in ADS, say in GR, that were teaching us about strongly coupled conformal field theories, giving us access to regimes where we had no other way of computing, in particular non-perturbative or strongly coupled regimes. So some examples of things in this category. So this is sort of, let's call this G1. There's a lot of examples of things that came out of this. Some of the early predictions and let's say triumphs of ADS-CFT, depending how you look at it, were predictions about the strongly coupled spectra of conformal field theories. So in situations where the ADS theory is a string theory, well, the bulk has strings, and these strings have a characteristic mass order the string scale. And so in, for example, the n=4 super Yang-Mills context, if we call the coupling lambda, then this string scale maps to this positive power of lambda, where here lambda is asymptotically large. So this is a prediction about the strongly coupled spectrum, which is precise. There's a power here which is precise and which relates to a specific kind of theory, and tells us that, okay, even when this coupling is strong, there are states whose mass we can predict from gravity computation, just from knowing the map between the string scale and the bulk and the coupling on the boundary. This was then confirmed by integrability approaches in n=4 super Yang-Mills some years later, and according to Igor Klebanov, who once told me that, well, people were sort of skeptical of ADS-CFT for a while, but then maybe when this integrability computation confirmed this prediction, sort of game over. So this ended up being important as a marker for what field theorists should try to find. And then in this case, in the n=4 super Yang-Mills case, they did find it, and this was unequivocal evidence for the correspondence. So that's a statement about operator dimensions, and I'll define things more precisely as we go along. This is still the introductory part. More robust quantities, like strongly coupled thermal entropies, were also predicted from ADS. So we have some thermal free energy at some inverse temperature beta. In general, would depend on the coupling in some theory, which I'll call lambda. So if we define this as minus the log of a CFT partition function on a circle, whose circumference is the inverse temperature, times flat space. Conformal symmetry dictates that this, in general, is given by this power of beta, d-1, where it's a d-dimensional CFT, times some function of this coupling lambda, And it's strong coupling, right? This is a hard thing to compute in field theory. Actually, the status of this in field theory settings is that this has been computed like in a controlled way to like second or third order in perturbation theory. That's the current state of the art. N equals 4 super Yang millis, say. But IPhT-TV tells you it's strong coupling, how this behaves. This gives rise to this sort of by now famous 3/4 vector, where this goes to 3/4 times the free value at strong coupling. Another very famous and interesting prediction of the correspondence. And there are other things like this, like the viscosity to entropy density ratio of a strongly coupled plasma. And let's also just put here one more, which I think is sort of important for this taxonomic type question. Even just the existence of certain types of conformal field theories was first predicted or strongly confirmed by IPhT-TV. So in particular, there are these exotic, let's say traditionally exotic conformal field theories which live in 6 dimensions, whose existence was speculated from some sort of string theory points of view, but then IPhT-TV showed us that there's a very simple gravitational background which predicts the existence of these things and tells us a lot of information about them. So even just the existence of theories themselves is something we learned from IPhT-TV in these early days. But then things shifted. So in this kind of cartoon of the history of IPhT-TV, things shifted around 2008, 9, 10, a little bit after that, so that we were learning things about ADS from CFT. For which one? You mean the early work pre-ADS-CFT that was trying to... Yeah, so there were these works by Aharoni and Seiberg, these sort of little string theory folks pre-ADS-CFT. And then, in Juan's original paper, he pointed out that there are these M-theory backgrounds of maximal supersymmetry, which should predict the existence of this field theory, which had been ascertained from these other stringy perspectives with less rigor. Yeah. Okay, so this course is sort of about this V2, right, where we're learning about bulk gravity, the space of bulk gravity theories, but also properties of bulk gravity theories from CFT. And this is all, well, this is largely in part due to the bootstrap point of view on conformal physics. So this is interesting and useful. So it's interesting because we want to learn about quantum gravity, and quantum gravity is a complicated thing to define. What the rules are hard to know, but part of the point is that you can get around these tricky issues by studying conformal field theory, which is more rigorously defined and doesn't have gravity and all the complications that come with it. So why is this useful? That's because CFTs are EV complete in the sense that you don't have this number normalization issue of the graviton to deal with. They exist. Okay, so we know they exist. They admit thematic definitions. By this, I don't mean that we know the minimal set of axioms which rigorously defines a CFT, but we know some things from which other things can be rigorously derived. And some of these axioms are no doubt true, and there are things about CFTs that have been proven where once one enters gravity, it's hard to know what the answer is. So there are axiomatic definitions of at least certain observables in CFTs, and one might optimistically say there's some axiomatic way to define a CFT completely, even though that's sort of unfinished work. But to that last point, they obey rigorous theorems. Theories of gravity also do, but harder to deal with, especially in the quantum context where space-time isn't well defined. Speaking of which, they have a non-gauge redundant notion of time, which is useful and should in principle help us resolve things like the black hole information paradox, because, well, unitary CFTs are unitary. And so if you can push this into the bulk, then you should be able to understand something about time evolution in the quantum setting, where then you can't point to a point in time in the theory of quantum gravity and talk about that meaningfully because of different variants. Okay. Yes.
I mean, the axiomatic definition is not understood. Do you have something in mind?
Well, yeah. So for one thing, I don't think in general dimension. Well, so first of all, there are different sets of axioms, right? And the relation between them sort of recently been better understood, but from what I understand, it's not fully, completely understood. So, there are some which are better phrased in Lorentzian, some Euclidean. What are we doing when we go back and forth between the two? Are we just using, do these capture the same information, even though they look very different, sort of axiomatically? And one kind of consequence of this, which, well, maybe it's a consequence of this, maybe it's just related. In general, CFTs in D dimensions, we don't know the minimal set of constraints one must impose on observables to guarantee the consistency of the full theory. Where in 2 dimensions, we have something like Moore Seiberg, which tells us that if you enforce the modularity of 0 and 1 point functions of the torus and 4-point crossing, then all other correlators will obey the necessary crossing conditions, and the theory will exist. In higher dimensions, we don't have the analog of this. And I think you could say that's a result of not having a complete axiomatic definition of the theory, because if you did, then you could try to say, well, here's a minimal set of things I have to impose on some subset of the infinite number of observables, and that is enough. And we don't have that. That's what I mean. On this line, there's these nice works by Kravchuk, Vychkov, and Shao years about relating these different axiomatic systems and showing that various Lorentzian properties of correlators follow from Euclidean properties. I recommend those works in this context for those who are. Yeah. Good. Other questions? Now we're coming to the end of the introduction. So this is why this kind of approach is useful to the extent that it can be implemented, and it can. And, well, just to reiterate, if we think about a general theory of quantum gravity, what consistency conditions it should obey, this is definitely a hard question to answer. And even in the context of string theory, I wouldn't say we know fully what the rules are or fully what string theory means, looks like non-perturbatively. And that's, the one theory of quantum gravity from which we've learned a lot and can really get our hands on. So even in that, it's not as if we understand string theory and we just are trying to make sure there's nothing else out there. We would also like to understand what it means to do string theory away from various simplifying limits like classical limit or field theory limit. Okay, so then that brings us finally to stating concisely what is the goal of the course, which is to give an overview of the space and the properties of holographic CFTs I'm going to put this in some blue quotes because I'm going to define what this means. Roughly speaking, this means some class of CFTs which have holographic duals by way of correspondence, which look nice. The bulk theories are simple theories of gravity. This is to be distinguished from this strong form of ADS CFT, where we imagine there's some bulk theory dual to every CFT, but usually we use the word holographic CFTs to mean those which have a nice bulk dual, Einstein gravity coupled to some stuff. So we're going to talk about the emergence of that nice picture in gravity from some operations on the field theory side. And so we'll talk about all that. That'll be one of the two major themes. And the other is to explain the role, significant as it is, of the conformal bootstrap in giving us techniques to do this, and also just getting us to think straight about it. Now, the last lecture, so let me talk about the plan for the lectures. So first, well, sort of basic extended introduction. We're going to talk about what data of CFTs are useful to specify, what observables we're going to study in trying to answer these questions, and the sort of definition of a holographic CFT that I just sketched. Okay. Next time, and so part of this will be sort of introducing the bootstrap philosophy. Next time we'll talk about some, let's say, holographic bootstrap results. Include some results about superconformal field theories where things are especially clean and exhibiting a relation between the bulk and the boundary. And we'll talk a bit more about the ADS CFT dictionary so we can take these results and understand them in bulk terms. Then in lecture 3, we will talk about how to compute 4-point functions holographically, because as it will turn out, 4-point functions of local operators are really valuable. They contain a ton of information about the CFT data. Say the 2- and 3-point functions in particular are all sort of hiding in 4-point functions, which themselves obey crossing relations. And so you can leverage those to understand this point here. How to compute 4-point functions holographically, this is something that people started to do right after ADS CFT was invented, but there's a nice history, there's some really nice techniques, and this will be important for lecture 4. Where then we will use these results, the constraints on the 4-point functions and the output of them to sort of understand where some of these results come from, and more generally how they can be abstracted to constrain the space and finally arrive at the picture that we now understand. Now, lecture 5, should I lower this? It's an interesting feature. It tilts back that way too, apparently. This seems not broken. Is that correct? Or did it break? No. All right. I'm going to proceed then. You want to raise it up? Oh, I'm trying to lower it. Is it okay? No. I was trying to lower it. I broke it, but then. What this is. This is interesting. Well, to be addressed during the break. So what is lecture 5 about? Lecture 5 will be about theories of ADS quantum gravity in 3 dimensions, which are dual to CFTs in 2 dimensions. So why devote a whole lecture to this? Well, there's a host of techniques that are applicable in this setting, which allow you to get stronger results. And the reason, ultimately, is that 2D CFTs are special. They're qualitatively different than their higher dimensional cousins because of the fact that the space-time dimension is lower. There's some simplifications, but there are also some enlargements and well, complications in a way. Symmetries are greater. So why is CFT2 special? Well, first of all, you have local rather than just global conformal symmetry. I'll explain what that means. In other words, there's an enhancement of the conformal symmetry to the full Virasoro algebra, or perhaps more. Perhaps there are more currents than just those that are realized in the Virasoro algebra. You also have the fact that the state operator correspondence puts the theory on the torus, and the theory on the torus must obey modular invariance. Which is to say, there's an SL2Z symmetry of any 2D CFT on the torus, which reflects that the choice of how you label the cycles of the torus is not a physical quantity. And this can actually be leveraged very strongly to relate the high and low energy parts of the spectrum, and more generally, observables in the high and low energy parts of the theory. This is a kind of UV-IR connection in the context of CFT2 that we haven't made solid in higher dimensions. And in the bulk, well, gravity in ADS3 is different from gravity in higher dimensions for a few reasons. The main reason being that it is effectively topological. There are no local, that is, propagating degrees of freedom in a theory of gravity in 3 dimensions. And if you put it in the space of the boundary, like ADS3, then all the degrees of freedom live near the boundary. So the graviton is sometimes referred to as the boundary graviton in ADS3. And so for this reason, the bulk theory is sort of easier to handle, but still remains non-trivial because there are black hole solutions, and you can have black hole solutions form dynamically by collapse. There's enough going on that you could actually hope to understand something deep about quantum gravity, even though there are simplifications. So ADS3 CFT2 is sort of basin of attraction for people who work on these types of questions a lot of the time because, you know, there's more power there. And there's more prospects of solving things exactly in a way that's hard to imagine. You might say something is lost because they're less rich, and you know that's a matter of taste. Ideally, one works on both. That's the thing. Good. So that's where we're going, and so let me pause and ask if there are questions. Then I will get into the sort of CFT data stuff. We'll take a break, and then we'll continue. But are there questions about this plan and the big picture?
In this drawing you are erasing, do you mean that spares and string are in bijection?
No. Yeah. So this was not so well drawn, let's say. So let me do a little better to answer this question. The answer is no. There's a question. There's this kind of driving idea in the community for some years now, which is this idea of string universality, which is that so most broadly, this is the statement that every consistent theory of quantum gravity must be string theory, one way or another. And that's hard to make precise. If you ask about theories of quantum gravity in ADS and restrict to those with classical limits, then this is something that you can really phrase a bit more sharply. Does every such consistent classical ADS vacuum belong to a string theory? And so we don't know the answer. We'll talk about this. There's some evidence that the answer might be yes, but it's a big claim, so one doesn't want to declare victory. But on the CFT side, one then wants to look for signatures of what that would mean, of stringiness. So that's something we're understanding more and more. We'll definitely get into this as the course goes on. But no, the sparseness and the stringiness were not meant to be one-to-one. Because, for example, you can have a string theory that is, when alpha prime is finite, then on the boundary, this is like a theory of intermediate coupling, where the spectrum is not sparse anymore. Yeah. I mean, yes. So yeah, sparseness is kind of associated with a GR type limit, where the theory is actually supergravity or Einstein gravity, not full string theory.
Those sparseness was eventually Hagedorn behavior, sub-Hagedorn behavior.
So in ADS, so in CFT2, the sparseness definition, due to Hartmann, Keller, and Stoica, is different from what I just said. Here I mean it in the more general sense of the light spectrum being as gapped as possible, especially in the higher spin sector. But yeah, in CFT2, the word sparse means something more precise. It includes Hagedorn growth, but I didn't mean it in that sense.
So the answer to his question depends on your definition of sparseness.
Yeah. Yeah. As we'll see, there's an important distinction between a spectrum of operators which in a large N theory, whether you have operators of Lorentz spin greater than 2, whose dimensions are light, say order 1, that ends up being an indicator of whether the bulk theory is general relativity or something more complicated like string theory. The spin is important for that statement. But you could also just ask generally about how populated the low-lying spectrum is without talking about spin. And the relation of that to whether the bulk theory is GR or something more complicated is not sharp. It also just so happens in all the nicest examples, there are relatively few low-lying fields of any spin, but that's a little bit of a lamppost effect. Okay. So, this is not a conformal bootstrap course, and it's not even really a conformal field theory course. So I'm just going to introduce the minimum of CFT data that I think we'll need to say what we want to say. And maybe I'm assuming some passing familiarity with this, but I think at least for most of the audience, that's box is checked. So, with that said, please ask questions. Okay. When I talk about operators in this course, I'm going to be talking about local operators the whole time. And local operators in CFTs are labeled by the Lorentz spins and await under dilatations. So the conformal group in Euclidean CFT is SOD plus 1, comma 1. And a rotationally invariant theory will have local operators that transform in irreducible representations of SOD, the Euclidean rotation group. Okay. So CFT will be in D dimensions throughout the course. There's an SOD subgroup of the conformal group, which leads to some spin quantum numbers J for a given operator. And there's a dilatation operator, the operator which implements scale transformation in a CFT. And this commutes, so the dilatation operator commutes with the rotation generators. So we can simultaneously give a label to all operators delta, which is their weight under dilatation. Now, the dilatation spectrum in flat space is equivalent to the spectrum of energies when you put the theory on a sphere times r. This is the state operator correspondence. So energies on space give the spectrum of dilatations three-dimensional Euclidean flat space. This is the statement of radial quantization, and a local operator is an eigenstate of the Hamiltonian and radial quantization. And I'll refer to these as O. So for me, local operators will be O, maybe sometimes phi. And the state operator correspondence is that if we act at the origin and radial quantization on the vacuum, then we generate this state. So we can use this language. And any such O is labeled by some spins and some dimension. Besides the conformal symmetry, there might be some other global symmetries, G, and these will come with some set of currents, which will have spins 1. These can be some flavor symmetries, or in the superconformal field theory, R symmetries, which are special currents that live in special types of superconformal multiplets. And in the superconformal case, you have some enhancement of the conformal algebra to the superconformal algebra, whose details we won't need for what comes. Now, by studying representations of the conformal algebra, in particular the action of the special conformal generators, K, you learn that there are primary states in the theory. So all the states can be organized into conformal multiplets. The bottom component of the multiplet, let's call this state at level 0, would be some operator O. Okay, so this has some spins J and some dimension delta. And what makes this a primary is that it's annihilated by the lowering generators, which you should think of as the special conformal generators K. So this is a lowest weight state. And we generate the rest of the multiplet, which is infinite dimensional, by acting with the raising operators, which are the momentum generators P of the conformal group, the conformal algebra. So mu runs from 1 to D. We act with P on this state, and we generate a new state. This is the descendant under the conformal algebra of the primary. This has dimension delta plus 1, okay? 2, yeah, with momentum twice, and so on. For this reason, when we talk about correlation functions, we only ever need to talk about those of conformal primaries, O. So that's what we'll do. And because of the existence of the operator product expansion, the full set of local operator data is given by, well, I'm going to suppress the spin dependence, but sort of, the labels of the operators, which are their conformal weights and their spins, and the 3-point functions, the ijk, among these operators, in particular the primary operators. We just need to understand this set of data for the primary operators. And this is the local operator data of the theory. So from this sort of limited point of view, a CFT is a list of data, of numbers. In unitary theory, these are real numbers, that obey other bounds as well, which obey some set of consistency conditions. Okay, so one wants to understand what these lists are allowed to be. Now, let me talk until the break about a few special pieces of CFT data that will be important for the holographic picture. So what operators is one especially interested in?
Yeah. Sorry, you also have the spins in the CFT.
Yeah, I'm just suppressing that. Yeah, I mean, it was just a stand-in for like the 2-point data in the spectrum. Good. So let me highlight two sort of sets of special CFT data. Okay. The first are exactly marginal operators. What are these? These are operators whose dimension is exactly equal to d, the space-time dimension. And let us assume that these also are scalar operators, so their spins are 0. This preserves Lorentz symmetry, so that's why we do that. So to form an action by some spinning thing, then you break the Lorentz symmetry. Now these are special because they generate a motion in the space of conformal field theories, parameterized by some continuous coupling. Let's call it T. So given some CFT action, if you look at the spectrum of that CFT and you find there's an operator with these quantum numbers, then you can deform the theory. And let's call this operator O. Okay, so I know that's the symbol I was using in general, but just for this discussion, let's also just refer to O as the marginal guy. And some coupling T in front here.
But sorry, but in practice, how do you prove that it's exactly marginal?
I'm assuming it exists, so that's a separate question. Yeah. But that reminds me to say, not every theory has this. It's just, if it does, then you can do things with it. In particular, you ascertain the existence of a line or perhaps higher dimensional space of fixed points. Yeah.
Are there non-supersymmetric examples?
Rigorously, no. And by that I mean away from, so in higher dimension, so in greater than 2 dimensions and away from some perturbative limit or some epsilon expansion or something like this. No. We don't know if conformal manifolds exist absent supersymmetry in more than 2 dimensions. Yeah. You know, there's some lore that they don't because there's nothing protecting the dimension if you don't have supersymmetry from getting some corrections as you. Yeah, it's that kind of argument, I mean, morally speaking. There are, on the other side, constructions in certain regimes that are, you know, indicate at least the existence of an approximate conformal manifold. This includes large N CFTs with holographic duals, where you can write something with a massless scalar, which seems fine, and maybe one loop protected or something, and other large N expansions in CFT. But at finite N, with everything else finite, no, there's no. And I exclude 2 dimensions because in 2 dimensions there are examples such as okay. Now I put this in quotes because I'm not assuming that the CFT is Lagrangian theory. There might not be an action. What this means is that if you have some observable, some correlator, then at least if you want to deform from that sort of point away by adding this operator, you just insert an e to the t integral O into that observable, and then you can, say, compute perturbatively in t. But in principle, this would define for you some scheme by which to compute the change in this observable away from the original fixed point. So it's usually written like this, but this is meant in a schematic way where we don't assume the theory is Lagrangian. So from a manifold, which I'll write as M, is the word often used for the space of theories parametrized by T, or if there are multiple couplings, some set of couplings T. So this is, by the way, some dimensionless coupling. So let me draw it like this. We have some conformal manifold M. If you start from some reference point here, T star, then you can compute observables elsewhere by inserting the e to the TO and doing your best to compute it. Usually one computes perturbatively, but the idea is that as you move in T, you're exploring this space. Okay? If T is real and there's one coupling, you can think of this as a line of fixed points. But often T is complex, or there are multiple couplings, so I'm drawing it in this two-dimensional way. Okay. So a familiar example is that O is a Lagrangian operator in a gauge theory, which happens to be exactly protected against some corrections, say in the presence of supersymmetry. This is the case, and I mean, really, the most familiar and robust constructions of these types of operators come in the context of gauge theories coupled to matter. Okay. We already talked about the existence of non-supersymmetric such things. That's a good question, which I was going to bring out myself. And why am I bringing it up in the context of this course? Well, because in any CFT, such couplings are not necessary, but they're often part of the canonical constructions. So, for example, one often takes a double scaling limit where, so here in this context, T would be the Yang-Mills coupling squared, like this, or perhaps a complexified version thereof. And so often we take double scaling limits, we form some coupling lambda, which is the product of T with some parameter n, and we take n to infinity and T to 0 with this product fixed. And this is what reveals for us the bulk theory in a limit of large lambda in some planar limit, having taken n large. So you need a coupling T to go to this type of regime, and often that's present in the constructions that we're used to. That's why I'm mentioning it today. But even in the wider realm of CFT, these are obviously very special operators because unlike an operator whose dimension is not exactly equal to D, they connect different fixed points. So they map out for you a continuous space of conformal field theory. If you deform by a relevant or irrelevant operator, you RG flow somewhere. Okay, so the other special operator, which is perhaps obvious, is the stress tensor, mu nu. So it's a symmetric traceless spin 2 operator. Traceless, okay. It's exactly conserved. Its dimension is exactly equal to D. And while there are slightly, let's say, niche conformal field theories that have no local stress tensor, we'll be talking about local CFTs in this course, which will have a stress tensor. In any CFT, this is important. The stress tensor is dual to the graviton, so we want this here. Good. The fact that it's conserved is the same statement that delta equals D. If you ask what the spin J unitarity bound is, where I take J to be a symmetric basis operator, it's this, okay? Where saturation implies an exactly conserved current. So this is the case for the stress tensor. Yeah.
What happens if we deform a CFT by an operator with delta equals to D but some spin J?
So we'll break the Lorentz symmetry, and so you won't have a full conformal or superconformal theory anymore.
It will still be scaling variant.
This is sometimes considered in certain contexts, but I won't consider it. As a side note, having mentioned the spin J unitarity bound, so if there exists, so if we look in D greater than 2 dimensions, if there exists a spin 2 current, call this an operator O, where the spin is J greater than 2, and the dimension exactly saturates this, let's call this J star. So if there exists this operator, then the CFT is free. By that I mean that the correlation functions are equivalent to those of a free theory. So we're already seeing here that when you look at the spectrum of operators of spin greater than 2, there are some strong statements that follow from the relation of the spectrum to the unitarity bound. In particular, if there's one current which saturates this, spin is greater than 2, then the theory is free. We'll return to that. Now, the stress tensor 2-point function, like all 2-point functions of all operators in conformal field theory, is fixed by conformal symmetry in terms of some tensor structure, which, following Dolan-Osborn, I'll call I, U nu rho sigma, divided by some power of the position, so x is 0, times some constant, ct. Okay, this is important.
It actually equal to this W from some.
Sorry?
If it actually equal to 2, these would be the WN sort of symmetries.
Yeah, right. And therefore, this statement doesn't apply because, as you know, that doesn't. These are interacting theories. It's all.
Can I ask you a question about this? So if you are close to the limit, is the CFT close to free also? I mean, you can do a perturbation theory on that?
Yes, yes. And even there are questions about in what sense you are close. There are two ways of being close. One is if you're close where the deformation, the deviation comes from some coupling, which is small or something, but you're at a finite end theory. It's a coupling in your theory. And the other, and that's usually what happens, say, in Yang-Mills, if you go near the free fixed point, you deform away in perturbation theory, and the currents are broken by this deformation. You can also think about a family of theories where the breaking of the higher spin symmetry is suppressed by some large parameter, like 1 over, or like n. So if the divergence of the current is down by 1 over n, then this is like even closer to being free, because 1 over n is large, and it's not sort of a perturbative parameter in the theory. This is called slightly broken higher spin symmetry. And the critical ON model has that kind of symmetry breaking. So at large n, the Wilson-Fisher fixed point is almost free in the sense that the higher spin currents are almost conserved, where the non-conservation is down by 1 over n, where n is large. So these are two different ways in which higher spin symmetry can be broken, and they lead to very different types of spectra. I should say here, this kind of statement was first proven in 3 dimensions by Moldesen and Zhuboyedov, and then generalized.
But where do Vasiliev theories break this?
Sorry, say again?
Do the Vasiliev type theories break theory? Or?
No, they're perfectly consistent with it. And in fact, their work was motivated by trying to explain the structure of the Vasiliev theories just from symmetry grounds.
So they correspond to the free CFTs.
Yeah, so the Vasiliev theories in ADS4 are dual to ON models, and there's a choice of boundary conditions in the bulk. One choice gives you the free ON model in the boundary, the other choice gives you the critical. And in the critical case, the breaking of the higher spin symmetry is down by 1/n. So it's a slightly broken higher spin symmetry. That's the name for what I described before, when the breaking is down by 1/n. But that's exactly what you get from Vasiliev in ADS4. So that duality was even more supported by this statement. And yeah, I mean, the motivation was kind of to like derive its inevitability just from symmetry. Okay. Quantity CT is a type of central charge. In even dimensions, it has relation to central charges that you're used to thinking about from anomalies. In general dimensions, it's just some constant that parameterizes the theory. So it's an important constant. In even dimensions, CT is proportional to the C-type central charge that you find in the trace anomaly. But in odd dimensions, or fractional dimensions, if you're willing to go there, it's an independent piece of data. Okay, so it's just some number. And sometimes it's referred to as counting degrees of freedom in a theory, but it doesn't strictly do that. In 2 dimensions, it does. In 4 dimensions, it's really the A-type central charge that does that. In 3 dimensions, it doesn't. So there's no CT theorem, in other words. In 2 dimensions, CT coincides with C of Samologikov. But otherwise, CT is just some number. But maybe morally, it is capturing the number of degrees of freedom as it appears in the 2-point function of the stress tensor. Okay. Now, what about those other central charges that I mentioned? And then we'll take a break just after a few more minutes. So it does not formally count the number of degrees of freedom, but instead, the A anomaly in 4 dimensions, or the sphere free energy, aka F, as it's called, in 3 dimensions. Count those things. And in 2D, CT and C just differ by a number, so indeed it actually does here, but not here. It's a bit misleading. So in a 4-dimensional theory, for example, you might ask, well, C is appearing in the 2-point function, but it doesn't count degrees of freedom. Where do I find this quantity A that does count degrees of freedom? And the answer is in 3-point functions. So in a 4D CFT, if you look at the 3-point function of the stress tensor, this includes a term that is parameterized by this constant A. So the message is that the 2-point function, which includes this number, which is not a number of degrees of freedom, but still an important number in the theory, and the 3-point functions, say in a 4D theory, of the stress tensor are capturing some sort of irreducible information, which is important. These are numbers which either characterize the number of degrees of freedom or something morally like that. And as we make holographic constructions, these numbers will play an important role. I'll continue this after the break, but we probably do that now. Let me ask if there's any questions before we do that. Okay, well. Okay, so there's a lot you could say about central charges and CFTs. I'll sort of refrain from doing so for lack of time. I give a slightly sketchy picture of what constitutes freedom and what doesn't. What I want to focus on for the moment are 4D CFTs, where we have this A, central charge, which counts degrees of freedom, and C, which is the same thing as CT up to a constant, which doesn't count degrees of freedom in the strict sense that it is not monotonic under our G flow from UV to IR, and is not stationary, at least not proven to be so. But these quantities are both important for holographic applications. So there are constraints on these quantities, and likewise on CT in general dimension. Right, some obvious, some obvious constraints. Yes, okay. So in general, CT is non-negative. It's the norm of A. Okay. That's true for C. Okay. If A is to count degrees of freedom, then in a unitary theory, it had better also be non-negative. Okay. But there are less obvious constraints on these quantities, now restricting to the 4D setting, which are these Hoffman-Maldacena bounds on A and C. So where are they? The statement is that the ratio of A over C is bounded. Right, bigger? Is that?
Maybe.
Yeah, sure. Okay. Good. So what is the statement? The statement is that if I look at the ratio A over C, bounded above by 31 over 18, and bounded below by 1/3. Okay, this is the case with. So you can't make A too large unless you scale up C as well, vice versa. Okay. Explaining where these come from is outside the purview of this course. They come basically from enforcing causality of the CFT. But they're true, and they're obviously very powerful because these are order 1 numbers that don't differ too much from each other. There are supersymmetric versions of this. So, for example, in N equals 1 superconformal field theory, this becomes a half on the lower end, and this becomes 3/2 on the upper end. If it's N equals 2, that becomes 5/4. And if it's N equals 4, then A must equal C.
Sorry, the bound you wrote first, is it known to be D-bound, or you might expect in the future to be improvement?
So you're asking if this is optimal?
Yeah.
Yes, it is. Yeah, thanks for asking. So the upper and lower bounds are both realized by different free theories. And that's a useful comment, I think, because we notice that A over C equals 1 is always allowed. Okay. And so that seems like a sort of special value. And the extrema are realized by free theories. So maybe the A over C equals 1 case is somehow strongly coupled theory or indicative of some extremal point in the space of CFTs. And in a sense, that's true. So comments, A equals C is allowed. Special. I also said that in N equals 4 as CFT, A must equal C. So that's another reason why it's special. And as one gets large, the other must get large too. Okay. The third comment is that in CFT, now relating the previous two topics, you can ask whether A and C can vary as a function of exactly marginal couplings. In general, supersymmetry or not, A cannot, because otherwise it would not be counting degrees of freedom. If you're moving along a fixed line, dimensions can change continuously, but not the number of degrees of freedom, the number of operators. So A should be invariant, should not depend on T, the coupling. In the superconformal field theory, more is true. So in general, dt A is 0, supersymmetry or not. But in the superconformal theory, this is also true C. Okay, this follows some superconformal word identities. So these quantities stay the same as you vary marginal coupling.
Now, can you give an example of a theory with any equals 0, which has A equals C?
Yeah, so that'll form the backbone of the holographic CFT definition. So one short way to say it is that any CFT with the Einstein gravity dual has A equals C, the leading order in large A and C. You can also construct theories where A equals C and the theory is not dual to Einstein gravity. Take that it's not strongly coupled, the spectrum is not sparse, there's a lot of low-lying stuff, just by composing free theories. So, right, if you took the free theory, so the free vector saturates this, and a free scalar saturates this or something. So if you take appropriate multiples of free vectors and scalars, then you can make A equals C, but that's just a silly thing, right? So, but from that example, we do learn that A equals C cannot be a sufficient condition for theory to be strongly coupled and holographic. But it is a necessary condition.
Just to clarify, the CT here you're talking about is the one 2-point function, not some CFT definition in terms of number of degrees of freedom.
Correct. Yeah. 40 CT and C just differ by some 40 over pi to the fourth or something like this for the same quantity.
Oh, they are.
Yeah.
And the A is coming from the 3.
That's right. Yeah. So in 4D, in any D, CT comes from a 2-point function, and an even D, that CT can be identified with a linear combination of the C-type Weyl anomaly coefficients appearing in the trace anomaly. In 2D, A, there's no A, it's just C. In 4D, A can be extracted from the 3-point function. 6D, A can only be extracted from the 4-point function, which is interesting because the 4-point function is not constrained by symmetry up to some numbers, depends on cross ratios, and is highly theory dependent. And so that maybe morally is why a 60A theorem has not been rigorously proven. So you need to imagine that A is hiding somehow in some privileged part of the stress tensor 4-point function. But like how you extract it efficiently by applying some operator to the stress tensor 4-point function is not really understood. So if we understood that better, I think maybe we'd have the 60A theorem that was rock solid, but we don't. But in 6D, the A theorem's been proven for super conformal theories, and maybe there are no non-supersymmetric conformal theories in 6D anyway. So there's this whole set of beliefs that you can find the place where you feel comfortable if you want. But I think it's still an interesting, outstanding question that's at least a formal question. Okay. So I've got about 40 minutes, and so I want to introduce the bootstrap approach to space theories and some of the questions that it tries to answer, and then sort of talk about the large end version of those questions, which will let us define a holographic CFT. And somewhere I'll have to stop. Let me get it to the board. Other questions? I'll erase. So the conformal bootstrap started, well, there are early incarnations back in the 80s, and it's had especially a long history in the 2D context. Here I'm referring to the general Z story, which then was revived in 2008 by Bertazzi, Richkov, Tony, and Vicky, and has sort of taken off and come to mean a lot more than what it originally. So the definition I'm going to give is that the conformal bootstrap approach constrains the space and properties of CFTs by imposing symmetries and consistency conditions alone. And let us put this in some contrast to trying to explicitly solve some list of models, or taking a Lagrangian and computing everything. That's not the idea. The idea is to ask, how can we abstract what we know about CFTs in a language which doesn't assume either Lagrangian or any other perturbative construction that allows for a non-perturbative definition of a theory, and simultaneously say something about what these theories are allowed to look like. And it turns out that one can actually do this maybe more efficiently than one would expect. On top of that, what all the consistency conditions are is a time-dependent statement, and over time, certain conditions have been proven to be required for every CFT, and actual practical results have been extracted from it. So, for those with some familiarity, crossing symmetry, which is a statement about 4-point functions, we'll come to next lecture or the time after, is the sort of narrow version of what one is doing when implementing the conformal bootstrap. You take a 4-point function, you impose this crossing symmetry, the associativity of OPE on this thing, and you constrain the data that lies with it. But the bootstrap is about way more than crossing symmetry, and so we'll talk about this all in due course. So this can mean crossing symmetries in 2 dimensions. It can mean modularity of torus observables. In general dimensions, it can also mean things like the bound on chaos, or basically equivalently a bound on the Regge scaling of 4-point functions. These are sort of boundedness properties that correlators must obey. And I'm putting them in this category because, again, you can impose them abstractly and notice that the data of a 4-point function or of a CFT must be bounded in some way which follows from this dynamical constraint. So it's a bootstrap constraint in that sense. So what are some of the more specific questions that the bootstrap tries to answer, as in some cases very successfully? The first, maybe the most canonical, forget about the interactions, the OP coefficients, just try to constrain the spectra of CFTs. So maybe you fix your dimension, you fix your universality class, you say the CFT has some global symmetry or not, we fix the dimension. What is the spectrum allowed to look like? So we have some kind of plot here in delta. This is the conformal dimension spectrum of local operators on the sphere. And here we have the vacuum, delta equals 0. Then there's some dimension delta star where the lightest non-identity operator sits. And you'd like to ask, what is delta star allowed to be? Can I make delta star very large? Can I make the lightest operator very heavy? Or must it be bounded above by some number? Unitarity bounded below. So the bound from above is the interesting one. So the question is, where can this be? And if the bootstrap establishes the bound, some dimension delta star, And that means that in this region, there must exist some operator star whose dimension is bounded above by delta star. This is the canonical kind of question the bootstrap asks. And often you see plots of delta 1 versus delta 2. These will be the dimensions of the lightest two operators, and there's some space which is allowed, or more precisely, some space which is not allowed. Good. So there are other questions you can ask about the spectrum, not just bounding individual operator dimensions, but universality about how the operator spectrum must be organized. So, for example, there's some sense in which it's been shown that CFT operators must exist in families which lie on trajectories which have certain analyticity properties. So if I plot the lightest operators at a given spin, then they must lie on trajectories, often labeled Regge trajectories. That's the nomenclature that gets used in some kind of analogy with other physical systems. Right? They can't just be scattered randomly as you vary the spin and dimension. They must lie on some analytic trajectories that can be ordered. And so this isn't a bound in this sense, but it's a constraint, which is rather stronger in a way, about the universal organization of the whole set of operators. Yes?
You first go to delta smaller than 0. Is there a reason for it?
Yeah, that's because it's not actually delta that's being plotted here. It's delta some subtraction. Okay. Yeah.
But I am supposed to only be considering positive delta.
Yeah.
And is it correct to say that the first comes from first types of bound come from the gradient bootstrap and the second types of bound?
Yeah, that's fair to say. Yeah, good. Thanks. But you know, the one that gets pretty close. But this isn't quite just Euclidean bootstrap. So suppose you try to attack this problem by solving crossing symmetry for a 4-point function. The original approach to this, we don't need anything more sophisticated than that, was to expand the crossing equation around this crossing symmetric point where the cross ratio is equal to halfway between the S and T channels. You just expand around here. But you're expanding in a complex region, cross ratio, such that in the end, you're proving some Lorentzian regime. You're not restricted to the case where Z bar is Z star. You can do better than that. And in fact, the strongest bounds come when you really push this by probing this larger regime. So
if you're going to fix yourself at the crossing symmetric point, but then extend a little bit into the Lorentzian region to get the best bound for the first.
Yeah, that I think is a
And the second
kind of summary of how things evolved. Yeah. Is that, we have
I guess it's an extreme Lorentzian regime.
Yeah. So yes. Yeah, but I'd say over time, it's been appreciated that the more Lorentzian you can go, the more you get out. And this picture definitely relies heavily on that. Also, you know, the light cone bootstrap, which is another earlier, simpler version of this statement, that CFT has to have a kind of universality, a large spin. That is really a Lorentzian regime ultimately, but it wasn't quite phrased that way in the original papers. But that too comes from some mixture of these kinematical regimes. Bootstrappers in the audience, do you agree with what I've said?
You can add that, the plots that you get from the Euclidean match very nicely with this Lorentzian picture. So, like if you can go on this line and they populate the line, they do agree. But the existence of the lines you can prove it just from
So, okay, we've talked about the spectrum a bit, and inevitably a lot is getting left out. I'm just trying to give the picture that we'll need to apply to the holographic context. But questions are certainly welcome, but it's not meant to be anything comprehensive. Nevertheless, it's interesting, so let me say a bit more. You can also constrain OP coefficients, the interactions amongst the local primary operators in the theory. So here we're talking about, what is the lightest operator above the vacuum? How heavy can it be? Here we can ask a similar question in the context of an OPE. So take some operator O, look at the OPE of O with its conjugate. Say. The identity will appear. And then there's going to be some other operator O star, which is going, or what do you call this? And here there's some OP coefficient, which CO dagger phi. Right? So we can constrain, first of all, how high we can push the dimension of the first operator in this OPE, and second of all, what its OP coefficient is allowed to look like. That must be it. You can make plots involving OPE coefficients too, and indeed the bootstrap does that. Notice that these both together include central charge bounds. Right? So you can make bounds on central charges, whether in even or odd dimensions, by implementing this type of program. In particular, if you were to look at a stress tensor correlation function, well, I explained earlier that the stress tensor low point functions contain, in even dimensions, this anomaly, the central charge data. And so bootstrapping that correlator gives you OPE bounds that can then be interpreted as central charge bounds. You can also ask about things like asymptotics of the spectrum or the OPE. So as they go to large dimension, what do the interactions, how do they have to scale with delta, say, as I take delta to infinity? What does the density of operators have to look like? In 2 dimensions, we have the Cardy formula, which famously tells us that if you go to asymptotically large delta, it takes central charge C. There's an e to the root delta scaling of the density of states. In higher dimensions, there are more possibilities because there are different spatial manifolds you can choose. And you don't have modular invariance to tell you the answer. This is still an active area of research trying to understand asymptotic statements for CFTs on different spatial manifolds, but that's another thing that the bootstrap type of approach can try to answer, and in some cases has. Even in the 2-dimensional context, what the analog of Cardy's formula is for OPE coefficients is something that only relatively recently, it's a nice work by Giannis and collaborators, has been established.
Can you say a couple of words what is known in 340
About which? Yeah. So if you have your 4D theory on a flat background, then there's some kind of universal generalization of Cardy for NED, which is like so 2D Cardy is the root delta greater than 2, then you get something like e to the delta to be b minus 1 over d. Okay. But if you put the theory on a sphere, then or something else, some other manifold, then it gets more complicated. And I think there's some work that's actually going to come out in the next month or 2 by this Caltech group about this asymptotic density of states. We talked about this at people in the audience saw this. But yeah, I think there's some version of the Cardy formula that is going to apply to those settings in 4D that is going to come. Yeah, should go back and watch this talk. But
Sorry, the Cardi formula comes from modular invariance. So where do these formulas come from?
so I think the, I mean, one way to derive the Cardi formula is not. But if we think of it as a microcanonical version of the scaling of the free energy with temperature, that's fixed by conformal symmetry to be linear in beta, and that's a canonical version of the same statement. In higher dimensions, conformal symmetry fixes the log of the partition function in flat space to be the temperature to the d-1 times something. And that, when translated to a canonical ensemble statement about the density of states, becomes this d-1 over d, I believe.
Sorry, can you fix the coefficient?
Yeah, so the coefficient I don't think is universal.
Okay, so the difference with 2D is that the coefficient, okay, of course.
Yeah, I believe I'm saying correct things. In the 2D case, of course, we know the coefficient, that's true. Yeah, I think this is maybe the distinction between 2 and higher dimension.
This sphere stuff that you said is somewhere on 9, and are they fixing the coefficient somewhere? Or?
Yes, I think so. Those who saw the talk, any memory of this? Yeah, yeah. There's a talk by David Simmons-Duffin at this KCP conference in January. So, we have 20 plus minutes, 25 minutes, I guess. Started at 10:15. It's like a, what's the?
Yeah.
I guess it's up to what people can tolerate past once it gets to the lunch hours.
Okay, strictly less than 12:30.
Yeah. Okay. All right. So this was the kind of bootstrap picture for finite and in general. I shouldn't have erased that. Sorry.
I think I put A equals C in your bootstrap also.
Can you input that in the bootstrap?
Yes.
Yes. Well. I mean, yes and no. So depends what bootstrap you're doing. So I mean, there's some quantities where A and C don't obviously appear in the stress tensor, like 4-point function. They do. So if you're trying to solving crossing for a stress tensor 4-point function, 4 dimensions, then you could put this in. That would be like saying, you know, what's sometimes done is specifying some low-lying data, constraining. So for example, we talked about the spectral gap bounding the dimension of the lightest operator or the lightest few operators. If you have a good idea of the dimension of the lightest operator, either from a previous bootstrapping or some other source, you can put it in, then bound the second one. And often that information leads to stronger constraints for the higher operators, at least until the parametrics get away from you. So yes, saying A equals C in a, say, 4D stress tensor 4-point function bootstrap, I think would have some consequences, which would be observable. Yeah. But the status, by the way, well, so there was a paper 5 years ago where the stress tensor 4-point function in 3 dimensions was bootstrapped, crossing was solved, numerics were applied, etc. Plots were made. Islands were not found, but plots were made. Nice plots, and in 4 dimensions, it's still. I'd say that's not a. That's not. The story is not complete. Yeah.
depending on the assumptions, I guess islands were found. I mean, you have to add extra assumptions, like some gaps. Or...
Okay, but islands were found if you added enough assumptions.
Yes.
Plus, it stuck out to me were not those, but sorry, I forgot. What? Islands were found. Islands were found. These days, that's the standard for the bootstrap. So. No island, no paper. All right. So now onto holographic CFT. Let me just say in words some of what is going to happen. Holographic CFT, in the sense of being dual to a classical theory of gravity that looks like Einstein gravity coupled to some stuff, must really obey two main properties. First is it has to have a lot of degrees of freedom, large n. Okay? And that is what makes it classical in the bulk. The second is that the low-lying spectrum needs to be sufficiently gapped, sparse, and in particular, there's going to be a condition on the spectrum of operators of spin greater than 2. And if the gap to the lightest operator of spin greater than 2 is parametrically large, then the bulk theory is not just some classical string theory or something else, it's classical GR. That's the basic idea. You have this large n, this large higher spin gap, and it's believed that those are the two necessary and sufficient conditions for the bulk to be Einstein gravity plus stuff. Proving that has been something that people have been working on for the last 10 years or so, and to a large degree that is proven. So it's a very nice picture, and the minimalism of this emergence of spacetime is striking. You just need to specify that the theory has many degrees of freedom, and that there's this one spectral gap condition, and everything else looks like GR. So in particular, the OP coefficients, the 3-point functions, the higher point functions of stress tensors, those will be those of the graviton as computed in GR. And all you had to do was just specify that the spectrum is sparse when you go to this higher spin sector. That's a theme we'll be returning to, over and over throughout the course. So the first requirement is that you need large n. This is the same thing. It's in large CT, or large A, or large C. Making this distinction is sort of useful because in the bootstrap approach, where we abstract things we know about specific theories to the general context, you might ask, what is n even? We should talk about numbers that appear in correlators. And as I told you, CT, or C, or A are such numbers. But n is usually something we associate with a rank of a gauge group, or some way of parametrizing the central charge, which may not be visible, strictly speaking, from this abstract bootstrap perspective. But I'm still going to talk about large n, use that terminology because I think we all understand this means a lot of degrees of freedom, but with the caveat that it really is best thought of in terms of central charges, variables of any CFT, regardless of what else we know about. So large n in field theory, when going into the bulk, means small Newton's constant G Newton. So in other words, a CFT with lots of degrees of freedom is dual to some classical theory of gravity in ADS. So in other words, CT, and ask, what does the holographic dictionary tell us it maps to in the bulk? Well, this goes like 1 over G Newton. Okay?
Sorry, but what is n actually?
I don't need n to make this statement, but should I reprise this distinction? Which aspect are you trying to get?
Well, it looks like there is a parameter called n.
There's really just central charges. But are you saying? Yeah, I don't understand the question.
So you mean large n as an expression, not that
Yes.
there is any n.
Yes. Exactly. There is, in some sense, an n. I'll get to that. For now, it's just an expression. I'm not at that level of refinement. Yeah, we don't need that. These are good questions. I think we're getting a little bit. Maybe just a little. So, in a bulk theory of gravity, if we rewrite the Newton's constant in terms of the Planck mass, or the Planck length, it's given by Planck, the d minus 1. Remember, d is the boundary field theory dimension. So the ADS is in d plus 1 dimensions. Check this. Okay. So it's 4, so d is 3, so this goes again Planck squared, which is real world. Good. Got it. That's what I do in my head every time. So large CT and small g Newton are inversely proportional. This is one of the basic elements of the NES CFT dictionary, and that's why this is a classical limit. Now, to study a large N CFT, one doesn't just, pick n equals infinity. That's not really what we're interested in. We want to maybe do a semi-classical expansion in the bulk, or just be more precise about what we mean by taking large n. So we imagine there's a sequence of CFTs. Let's call it Tn, where for every n, there's a CFT. Okay. And the holographic CFT, let's call this T infinity, is somehow the limit of n equals infinity Tn. So we have some space of theories. We make up some label n. Okay. We have some sequence parameterized by n. And we take this sequence, we take the asymptotic limit in which the central charge somehow depends on n and is becoming larger and larger until we go out to infinity. This is a slightly more rigorous way to say what one is doing when one takes large n. There's a sequence of theories in which you take the central charge ever larger, and n is the thing that labels the members of the sequence. In the context of a gauge theory, n might be the rank, and then that's a specific realization of what I'm saying.
Of the assumption that somehow your space of theory is really one?
No, because it could be that each of these is a fixed line. But then, in that case, we just have to say what we're doing with the coupling, and then that gets us into the second criterion for holographic.
If I just do some sort of abstract bootstrap reasoning, how do I know that the space of sort of comes in such sort of degree?
Yeah, good question. So, we don't fully know that. Okay, so first of all, let us restrict to even dimensions. Okay. In 2 dimensions, Homological proved the C theorem. And one thing that implies is that C does not depend on any continuous parameters. C can't depend on exactly marginal couplings. As you move around a conformal manifold, C is fixed. And modulo one assumption, it implies what you're asking about. C can't depend on continuous parameters, full stop. So that means that there's not a continuous family of theories which obey the assumptions required that led to this result. Now, one of the assumptions that led to this result was that there's continuous parameters associated to some local deformation. And so in that sense, it's kind of building in like a Lagrangianness, if you like, of this deformation, the locality of deformation, which really amounts to saying that it's an exactly marginal coupling and not some other more exotic thing you could think of. You might say, what about Liouville theory? Liouville is a funny case because it has this central charge, and the Liouville action has this potential that, then B is not quantized. There's a CFT for every value of B. So I can vary B, and then the central charge seems to change. But the variation of the action with respect to B does not bring down a local operator. This is not. This is consistent with Zemlogichov's result. But it begs the question, why, in what precise sense is Liouville an exception? The statement, is it because the spectrum is continuous? Is it because it lacks a normalizable ground state? An interesting theory from different points of view. But still, with some mild assumption about what this continuous parameter is allowed to be, then C must be discretized in 2D. In 4D, we should really talk about A, first of all. And yeah, I don't know any rigorous argument that A has to be discretized. A cannot depend on exactly marginal couplings, but we want more than that. If we stick in the 4D context to SCFTs, then, well, we know that neither A nor C can depend on these marginal couplings. Still, for example, if you look at the 4-point bootstrap in a superconformal theory of some correlation function, you don't find that there are only solutions when A takes specific values. They can be bounded, but in that context, you can treat A as a continuous parameter and you find nothing. In other words, the crossing equations are analytic in these parameters. It's an interesting set of issues. Okay. So, let me hurry up a little bit. So when you take the large N limit, 1/n expansion, we can do, and you get this notion of single trace versus multi-trace operators. In gauge theory, these are operators that are like, well, involve a single trace over gauge indices, whereas multi-trace would be something like some composite of two operators like this. More generally, though, there's a distinction between different operators with different 1/n scalings in the OPE. So single trace operators you can think of as kind of like the operators out of which all others are built. You can take composites of them, and if you look at correlation functions involving those composites, there will be suppression by extra powers of 1/n. It's always useful to think back to the gauge theory context, where there's literally a trace, but the abstract version of that is just a statement about 1/n suppression of correlation functions.
So do you always need to have extra symmetry, which depends on N?
No. N's just a label. And really, once you get out to large N, if you think of this just as some kind of technicality for how you should think about going what large N means, then we can think about CT, and this is really one of our CT expansion. C expansion, etc. Okay, so the single trace operators are kind of the fundamental ones. We'll talk about the ASCII dictionary next time a bit more, but in the correspondence, single trace operators in the boundary are dual to elementary fields in the bulk, and multi-trace operators in the boundary are dual to composite operators in the bulk. So that's a sense in which the bulk sort of explicitly realizes the fact that these are elementary fields. Now, is this enough to get a holographic CFT in the sense that we described before? No. So what does this theory T infinity or holographic CFT look like? And the answer is it depends. and morally speaking, on the coupling. So the message of what the next 10 minutes will say, to conclude, is a large N theory that's strongly coupled, a large N theory that's weakly coupled. These are obviously very different, and their bulk duals will be very different correspondingly. And that's where this gap condition thing will come in. So I think it's still, despite the lack of time, useful to give a couple examples. So the ON model in 3 dimensions and large N is a theory that is not holographic in the sense that I'm talking about. So the critical ON model, Wilson-Fisher fixed point, is just ON invariant theory of n free scalars, the free ON model, plus a 1 over n deformation. So it's almost free. And this is this slightly broken higher spin symmetry thing that I said before. This is true at the level of the actions, but also at the level of correlators. You can establish this in some rigorous way. The statement that divergence of higher spin currents is down by some power. Now, if you look at the spectrum of this theory, it looks very different from the kinds of holographic theories that we will then talk about. So in the ON singlet vector, well, so here we have some field phi I. We can make bilinears, phi I, sprinkle a bunch of derivatives in between to make some spin J primary operators, where for a real scalar, the spin J is even. Okay. So at spin 0, it's just phi I squared. Right? Spin 2, you have the stress tensor. And then you have all these higher spin currents, which are approximately conserved. Now, these operators are sort of the analog of single trace operators, because we've taken a bilinear of 2 of the phi's to make a singlet. And you can make higher singlets if you want by taking composites of these. Right? But this is sort of the smallest thing you can do with the elementary fields phi I to make a singlet. So in the UI model, these are the analog of the single trace operators. But if we were to plot, the trajectory of these things, then they're almost exactly linear, like a free theory would be. So if we take, so let's take this to be delta equals 3, we take that to be spin 2, the stress tensor, and there's some operator whose dimension is, it's got spin 4, dimension is almost exactly 5, it's almost conserved. Likewise, spin 6, 8. This trajectory is almost exactly linear. And there's just one. If we restrict to singlets that are not multi-trace, that don't have more than 2 phi fields, there's just one such trajectory. Okay. And this is a theory that is dual to this ADS4 Vasiliev higher spin theory that was mentioned before. That is emphatically not a theory of general relativity. You have lots of higher spin gauge fields in the bulk, one for each such current, and that's very far from the holographic definition we're trying to get. But it's a large N theory, so something more is needed. Yeah.
When you mentioned the 1 over n expansion, do you also want to say that the fact that you need some sort of factorization property, so you should have under any cutoff, you don't want the number of these to scale with n?
Yes, for sure. So yeah, thanks. So that's part of the existence of this theory in the first place. So I would say that when we define this limit, one requirement is that if you look at the partition function on the sphere, the degeneracy of states below any fixed delta be finite. If it scales with n and n is going to infinity, then this theory does not exist.
And I can
Partition
take
function
n
is
copies.
infinity.
So if I take n copies of some CFT, that doesn't satisfy your. I can certainly think of a CFT to the X, right?
Yeah, you can. Well, so if you want a single stress tensor, then you will need to mod out by some stuff, and that will effectively lead to this property that I'm insisting on. If you don't do that, then yeah, then you just get infinity times the number of fields you started with, and that's just for me, that theory doesn't exist in the sense that we want.
That's fine. I just thought it should be said that it's
Yeah. Uh-huh. Yeah, I guess I would say that was hiding in here. And now the second example is this n equals 4 superconformal Yang-Mills theory in 4 dimensions. We'll talk more about this next time in a bit more detail, so I'll be more careful in explaining what this theory looks like. Invoke the mechanics of the supersymmetry as little as possible. And usually, this theory at large n is studied in the Tupf limit when people talk about stability or planar emergence or ADS5 times S5. And this limit is a theory where n is going to infinity, n is going to 0, and lambda, b squared n, is fixed. And as we know, in this limit, the theory develops a genus expansion, and at leading planar order, the observables depend on lambda, but lambda can be dialed to be small or large. So observables O depend on lambda. So let me say a bit about what the theory looks like, depending on whether it's weakly or strongly coupled. So this is schematic. So lambda equals 0. Well, the theory is free. Okay? That's as if you just take g to 0 first and then scale n to infinity. So the theory is free. This is just some supersymmetric fancy version of like what we were talking about over here, where you happen to also have gauge fields. So there's free. There's a higher symmetry. It's even bigger than the one over there because with the gauge indices, you can make more single trace operators out of the elementary fields. You have matrix valued things, so there's more indices flying around. You can contract them in different ways, and this leads to sort of a squaring of the sides of a higher spin algebra, if you like. And there are many light operators as a result of this, not just the currents, but many other ones. Okay. And so this theory, right, in the ADS-CFT dictionary, so just allow me to say, this is dual to not supergravity in ADS-5 times S5, but some sort of tensionless string theory in ADS-5 times S5, a highly stringy regime, not at all like unstandard. But if I take lambda to infinity, then the theory becomes very sparse. It's strongly coupled. Coupling. The spectrum becomes very sparse. Many states are lifted. And in particular, let me just highlight, whereas here you had lots of sort of singlets into the global symmetry whose dimensions were order 1, those operators are the ones whose dimensions grow, like lambda to the 1/4 at large lambda that I mentioned before. For example, the Konishi operator, for those who are familiar with that terminology, that's just the n equals 4 super Yang-Mills analog of this phi I operator. There's a scalar phi in the adjoint representation. I take trace phi squared. This operator requires a huge anomalous dimension at large lambda. And so, because of this decoupling of many states, the light spectrum is sparse indeed. And this is the regime which is dual to supergravity. On this famous AS5 times S5 space. Again, we'll say more about what all those words mean tomorrow or next week for those who are not. So what is the message? The value of the coupling lambda matters for what the bulk classical theory looks like. And the abstraction of coupling to situations where you may not have exact promotional coupling is this statement I made before about the higher spin single trace gap. So I'll conclude with this. Strong coupling is that theory is a large single trace higher spin gap. If I define delta gap as the dimension of the lightest operator spin greater than 2, which is single trace, then this must be very large. In the ADS5 times S5 context, it's always useful to keep this in mind, so we're going to talk about this next time. Again, just in as supersymmetry agnostic terms as possible. These modes that become heavy, that are higher spin modes, are the higher spin excitations of the string. So when you have a bulk string theory, the string famously has these regular trajectories of higher spin excitations, and the regime that's relevant for recovering supergravity at low energies is the regime in which all these higher spin stringy modes decouple. And the field theory statement of that for an arbitrary large N CFT, whether you know it's string dual or not, whether you know anything about it or not, is that the single trace gap in the higher spin sector be parametrically large. So, in view of time, let me stop there. I was hoping to draw a picture about the possible spectra. I think would tie this together, but I've gone a little bit long. People want 5 more minutes or not? All right, people want that picture. So people will get the picture. Okay. So I think this will tie this together. So let's again make some axis in delta. And there are a few different regimes that are relevant for holography. So there are 4 regimes, 4 different types of operators that are dual to 4 different types of states in the bulk. The regime where the dimensions are order 1. These are called light operators. Okay, this is where stress tensor is a light operator. There's a light scalar field whose mass is order 1 in ADS units. It's sort of living down here. So you have some field phi or something, mass, ADS units. These are perturbative particles. As you start to move up in the spectrum, you get to dimensions of order this delta gap scale. This is sort of the first regime, the light regime. Here we have, let's call it the stringy or higher spin regime. Okay. This is where these higher spin states start to come in. Okay. And any other states that might have been gapped by the same scale, like this Konishi operator. So these are more like states which strings, not local fields. And of course, in an agnostic picture radius CFT, there might not be strings in the bulk, but in situations that we understand the string theory, scales will coincide with these higher spin excitations or stringy trajectory excitations. So you have some re-entry in the spectrum of these heavy operators here. Now out here, I'll skip this for a second. When the dimension gets of order to central charge, since the central charge is 1 over g Newton, this means that you have a large back reaction in the bulk of whatever you might have put in the vacuum. So you can think of it this way: you start with a vacuum, you put some stuff, you put enough stuff that it back reacts very strongly. That happens when the energy of the stuff you put in is of order the characteristic scale of the bulk effective field theory, which is the Planck scale. And famously, this regime includes black holes. The black hole spectrum starts at delta equals CT times some number which depends on the setting. The number is order 1. So this is the black hole, or sort of non-vacuum geometry regime. Okay. And there's this third regime in between, where you have operators whose dimensions scale with some fractional power of CT less than 1. So this is large, but it's not as large as the scale needed to back react and make new geometry in the bulk. And so these are like heavy, but not that heavy. Sometimes this is called hefty, which is sort of a silly name. In ADS3, well, that name usually applies to ADS3 more than higher dimensions. But anyway, in the context of higher dimensions, this is where you might have D-brane excitation. So in the n equals 4 super-Yang-Mills setting, you have operators whose dimensions scale like root CT that are dual to D-brane operators in the bulk. So these are extended objects which are heavy, but not that heavy that they back react and make a new geometry. So let me just draw this schematically like this. Okay, so you have some big thing in the bulk, but not too big that it destroys the interior. And I'm using this stringy language, which is not meant to indicate that the bulk theory is always a string theory, but just as a guide for the mind in situations that you may be familiar with. You have the light stuff, you have the heavy higher spin stuff, then you might have non-perturbative stuff, and then eventually every theory of gravity has black holes. You always get them when you go up to the appropriate power of the Planck scale given by 1 over g. So holographic CFT, what is it? It's a scale where it's a theory where this is large, and this scale is also large. Okay. So I think I'm done. Are there any questions? So please ask them. And Hi. Yeah. Yes. So I mean, it is sort of by definition in a way, because the higher spin gap is a statement about the single trace operator dimensions. And the single trace condition is something that is a 1 over n counting condition. So maybe said a little differently, there are these techniques that you're familiar with, a lot of dispersive sum rules, where you can show that delta gap is bounded above by some power of CT, but they sort of come, in a way, they come from assuming this parametric separation in the first place. But yeah, there was an argument along these lines in Simone's solo paper. And morally, again, in the string context, this is like saying that so delta gap is the string scale, M Planck is Planck scale, and you can always arrange these scales such that M string is parametrically lighter than M Planck. That's the abstraction of that.
I just wanted to ask whether Wilson loops are in the category of hefty or stringy.
Well, strictly they're not even on this plot, right? Because here I'm plotting delta of local operators. Well, I guess by the time I get up here, it's going to get a little bit fuzzy with that means actually. Yeah, I guess I'd say they're hefty, but maybe they are within the error bounds of the meaning of this plot. But, yeah. In other words, right? Once we get up here, we shouldn't just think of this as a spectrum of the single trace operator dimension, because the notion of single trace breaks down for dimensions of order n, right? You take more traces than that, and you can rewrite as a multi-trace. So this is really up here. This starts to get more general than just a single trace spectrum. But yeah, Wilson lines are. Yeah, so in the n equals 4 context, yes. But in the abstract sense, you might just say, you know, there are sometimes operators whose dimensions scale as CT, but with a power less than 1. And I'm just carving out a region for them here to note that they're qualitatively different and that they don't induce back reaction.
So do you want to apply the label single trace to the
No, not really. No. Yeah, thanks. This is an imprecision of this map, but
Multi-trace operators appear where? Is it?
they're not appearing here at all. So they're just composites of everything that appears.
So but they can appear below the. It's important that it's a large single trace.
Absolutely. Yes.
This N.
Yep. Yeah, this is so if you were to have one light operator, then you can make composites with arbitrarily large spin. Certainly, spin 4, that would be a light operator still. The anomalous dimension is suppressed by 1/n because it's multi-trace. So you have many multi-trace higher spin operators which are light, but you have even a single trace operator which is light. That's why the single trace.
Now, from this, it still sounds like if you have a multi-trace operator below. First of all, is this possible? You can have a multi-trace operator below this lightest J equated to a single trace operator.
Yeah, you always do. You always do, in fact, because right, you have the stress tensor. So then make two particle, a double trace state of the stress tensor. Okay, a 2 graviton composite, which has spin 4. The dimension will be 2D plus 1/n correction, and so on. So you always will have light multi-trace higher spin guys. It's the single trace that matters, and this is intuitive from the bulk point of view because the single trace operators in the boundary map to elementary fields in the bulk. So you're really talking about the spectrum in the bulk of elementary fields. Yeah.
Well, largent factorization, is it actually an assumption that we're making on the space of largent CFTs, which is realized by all the examples we know of, or is it something that can be proven?
I wouldn't say I assumed it, but it's not proven that it always holds. Yeah. I did invoke it, it's true, at different times to say that there's a uniform suppression in 1/n of correlators with multi-trace operators. There can be some variation in that statement, but yeah, let's leave that to the side for now. But indeed, it's not some proven statement that any large N CFT must also have the strongest form of large N factorization.
Did we mix like some operators to have larger factorization and some other? No.
I guess so. I mean, I don't know. As far as we know, maybe. Yeah, I mean, the proposals of people trying to understand this type of setup involve things like that. The graviton sector, large N factorized, but maybe there's another sector which is not.
for now. Okay, now let's take